Good morning, everyone. It is indeed morning. Welcome back to COMP1511. Today, oh, thank you, Tom. I forgot to actually check. I've just got all these rituals of check if the audio is working and all this kind of stuff. And today I was just like, oh, I was just gonna roll into it. I always wonder if I should be like those YouTube channels that have like this specific greeting that they always have, and maybe I should have theme music that plays at the beginning before I start talking, but I'm not sure. I think that might be pushing things a little bit too far. Yes, I'm on YouTube, but this is slightly more of a functional thing than a purely entertainment YouTube channel. So, couple of things to talk about at the moment. One of them is the sort of changeover of assignments that's happening right now. So your first assignment is in the process of being marked. Some people actually have complete marks already, because your tutors are going through at the moment and hand marking all of the assignments, which means some of you will actually have your marks back already and complete. Other people will be waiting because, the tutors aren't just going to mark them all in one go, but we are, basically, the second the tutor finishes marking your assignment, you're going to get to see it. The first pass of the marking is the auto marking. So if you don't have a final mark, but you can see some information when you view the marks on your assignment, that'll be the auto marking that the computer has done. If you see any issues with that marking, you can email us about that, especially because, I've already had a couple of conversations with people who noticed. They've emailed me and said, look, I'm really sorry, I obviously left out something here, and yes, it's because I didn't test things completely, but here is the thing that I left out, and it's honestly it's about 8 characters worth of code. But at the moment, because of these little 8 characters worth of code, I've failed all of the auto tests. We can have a look at that, and we're not necessarily going to give you 0 for the whole assignment in that case. If we see that someone's done a whole lot of work and it's just a little bit of a change that needs to be done, we can help out with that change. You're not going to get all of your marks, obviously, because whoever hands in something that works off the bat and doesn't need to be changed at all is obviously going to get all the marks. But you can still get the majority of them. We're not just going to throw you in the bin for a couple of characters out of place in what is otherwise a completely functional assignment. So we're not cruel and vengeful gods. If we see that you've done the work, we're going to acknowledge that. Ooh, wow! Just looking in Tom's message there that about 100 people have complete marks. That's impressive. Oh, wait. About 100 people have the marks that have been finished. I thought when you said complete marks, I was 100 people got 100% in the assignment? It's that's pretty high. Anyway, the other thing that is happening at the moment is the second assignment has been released. The second assignment is called Castle Defense. I suggest that you just have a look at the theme of the assignment, even if nothing else, because we enjoyed putting this one together. Tom did a lot of the work on this one. Yeah, Tom, I get it now. 100 people have been marked. Not 100 people got 100% in the assignment. I think if we'd only marked a few of the assignments so far, and 100 people had 100% in the assignment, then that would be a problem. I think that would be, I'm setting an assignment that is way too easy. What was I going to say? Yeah, so the second assignment is a kind of a simulation of the tower defense genre. So it's not exactly, obviously, nothing we're going to do is going to be a complete implementation of a game genre or anything like that. Games tend to take more than 3 weeks to build. Although, if anyone's into game jamming you know, some games take 48 hours to build. They're not necessarily that polished when they come out at 48 hours, but you get some really cool concepts out of that. But castle defense is going to simulate the idea of little enemies moving across a fixed path, and the idea that there are towers that attack them as they go along that path. If they manage to reach the end, they do damage to our sort of home base, which is our castle. I'm not going to spoil it. I'm going to let you read it because it's funnier. Just check out the theming of it. We're pretty happy. Like we did some last minute changes to the layout of the kind of the characters involved because of some some recent events that have happened around the university, and we thought it would be quite funny. Okay, so Michael's saying that when you read over the Assignment 2 spec, you glazed over trying to understand it, and that is totally fine. Is that it's a lot about linked lists, and as it was with Assignment 1, what tends to happen is when we release the assignment, which was literally only 2 days ago when we released the assignment, we haven't necessarily taught you everything that you need to know about it. Having said that, you will notice if you've looked at the assignment, it has multi-file projects in it. It has 2 different ways to compile with the multi-file projects. It's all based on linked lists. So you'll need structs, pointers, memory allocation, and knowledge of linked lists to be able to do it. Our knowledge of linked lists is a little sparse for the moment because we've only just started them. But this entire week, when I say entire week, it's only 2 lectures every week. But these 2 lectures are just going to build up our capability to use linked lists. So over the course of last lecture, this lecture, and the next lecture, we're going to build an entire linked list example where if it had been based on what was in the assignment, the stuff that I'm doing in these 3 lectures would probably add up to about a credit in the assignment. So we're going to be focusing quite heavily on this. I'm going to be talking about the theory of how linked lists work and things like that. And the assignment and the lectures are very similar. They're not the same, obviously. If I did the assignment in lectures, I think that would be boring for people. The problem to solve in the assignment is different, and you'll have to think about how you apply linked lists to that. But hopefully what I'm going to show you is enough information that you'll be able to understand how to piece it together so that you can get your assignment going. If anyone is having trouble getting the assignment going, or anyone just wants more information about Assignment 2 and linked lists, I will be doing a bonus live stream on Friday. It's very similar to the last bonus live stream I did. I'll have a limited amount of slides which talk about the assignment itself, but then I will be answering any questions people have about linked lists. I may do a small code demo, or at least look at some code. If I'm going to look at any code, I will not necessarily do any code that's linked to the assignment, but I might go back to the example that we're going to hopefully have finished by the end of the day on Thursday this week, and then we'll look at this example and how it fits together. And if you're smart enough with your questions, you can kind of ask, in a sense, how we would apply some of the techniques from this example to slightly different questions, and then you'll get some clues about the assignment, that kind of thing. Right. Yes, people are asking in the chat there about the different kind of marks for Assignment 1 and Assignment 2. So Assignment 1 is reasonably low marks, Assignment 2 is higher marks. The reason behind Assignment 2 being more marks than Assignment 1 is not necessarily that there is more quantity of work. Assignment 2 has more difficult concepts to understand. The other reason for this is the notion of sort of learning and feedback, in that the first assignment, it's quite easy to get stuff wrong in the first assignment because we haven't established our conventions of how we want to work and things like that. So you might get some feedback in the first assignment saying you should probably style this differently. And in that case, you may feel like you lose marks in the first assignment, but that kind of feedback will lead you to getting higher marks in the second assignment, which is worth more. So it's kind of like the first one's a tester and the second one is the real challenge. That's why it's worth more. Also, I feel like this second assignment, if you do badly in the first assignment, but you can do well in the second assignment, I allow the second assignment to sort of overrule the first assignment, because the second assignment uses a lot of what we need to know about working with C code. It's slightly different because the first assignment's based on arrays, the second assignment is based on linked lists. So there's no use of arrays in the second assignment, but you still have to do looping and things like that. So it's nearly everything that we've covered in the course is in the second assignment. Not quite, but nearly. Enough so that it's worth putting more marks into the second assignment. I think we've also already started getting a few questions about the exam. I'll talk more about the exam later. I don't necessarily have time in this lecture to talk about the exam, but I will find some time to answer questions about the exam. We are also doing an entire lecture about the exam and revision. It might be an entire lecture. It's either an entire lecture or it's like one of my internal, in my head, lecture components, which is like about an hour long about it. So I will definitely be covering that, but not just yet. I would say for the moment, please focus on the second assignment for the moment and then the exam later. Because when you consider the exam's worth 45%, second assignment's worth 25%, that means the second assignment's still worth thinking about. Don't skip your brain over the second assignment and to the final exam just yet. But I will definitely be talking about it. And Tom said that he's answered a whole lot of questions about the exam already on the forums, which is handy. So check the forums if you want. And yes, in the same way that I do a bonus live stream to talk about specific assessments, and I call them bonus live streams because they're not compulsory. They're not content that you really need to know. The lectures are always content you really need to know, but the bonus content is like, let me just help you with this particular assessment. There will be a bonus stream at some point during the study period that will talk about the exam, and we'll just kind of answer anyone's final questions about particular topics and things like that. Again, none of that stuff is compulsory, but you might find it interesting to get some information like that. So up to you how you decide you want to use the extra things in the course. I think a lot of people will just want to see the minimum amount of content in the course, which is just the lectures and tutorials, and then do the labs on your own. But other people are going to want to spend more time in the lab so they can get one-on-one time with their tutors. Other people are going to want to come to all of the live streams to get specific information about assignments and things like that. But up to you, you know, like how much you consume the unnecessary but useful content is up to you. Okay, let's get into this particular lecture. I've got some things I want to talk about today, and we're going to do a lot of live coding today. I mean, there's theory, there's diagrams, as well as live coding. Okay, so last week, this is like probably one of the busiest last week slides that I've done, is that we did memory allocation. We had a quick look at multi-file projects. We threw in command line arguments as well. Command line arguments are something that are handy to know, but there's usually kind of other ways around the problem. I mean, I would still know where to look them up if I were you, and we'll do some tutorial and lab questions on them just to make sure that you've seen them, but they're not nearly as important as learning about linked lists. So command line arguments are things that will potentially happen to some programs that you might write in the future. Linked lists and the theory surrounding them about how to have a data structure that joins up identical nodes together is definitely going to come back again, and is one of the fundamental core elements of the theory of computation. So, so when it comes down to it, you know, when I'm saying what's the difference of importance between these things, linked lists are super important. But command line arguments less so. Multi-file projects are going to come up all the time, but they're not always going to be in exactly this format, depending on the programming language you use. So I'm kind of saying that these are secondary things, but linked list is like super important, which is why they get a little piece of one lecture and linked list gets 3 lectures. So it's a big deal, and we're going to put more effort into this. So today, this is short here, but we're going to spend a lot of time on it. So we're going to continue the Battle Royale example that we started last week. And we're going to start looking at adding and removing from linked lists. I don't think we're going to do removal today. I think removal's Thursday, but we're going to start adding today, and we're going to start looking at different ways of adding. I had a question in the lecture last week saying, are we always going to be adding just at the head of the list? And it's like, no, we are not just going to be adding at the head of the list. We're going to look at other ways to add to a linked list. I can't remember if we were going to do it today, but we're also going to try to add to a linked list by finding a position in the list we want to add to, and then pushing it in there. I'm pretty sure we are going to do that today. We'll see what we have time for. Oh, I remember also we had questions last week. Last Thursday, someone had asked me to do some detail on fgets and fputs, and I remember pressing the button on the stream that turned off the stream just as the comment came up reminding me about that, and I was like, oh, because I'd reminded myself of it like 2 or 3 times during the lecture, and then when it came down to it at the end, I just pressed the off button, and I turned off the stream just as I was like, oh, there was something else that I was supposed to do. So, if you're here, I can't remember who it was, I think it was Ray, but I can't remember. Yeah, if you're here, we will, I can do that after the lecture today, if you stick around afterwards. Obviously, anyone who sticks around afterwards who wants to know more about linked lists, you can stick around and ask questions, because I have a feeling that people are going to have a lot of questions about linked lists. Linked lists are kind of the pinnacle of the course at the moment, because they're one of the sort of fundamental data structures for computation, and they take a lot of effort to learn about, and they'll take a bit of practice. So we're going to throw a lot of it at you at once. We're going to do a lot in tutorials. We're going to do a lot in the assignment. We're doing a lot in lectures also. So it's all going to basically try to give you as many opportunities as possible to learn about them. So if there's anything missing in what you think you know about them, we'll try to give it to you as much as you can. Alright, I'm just looking in chat. There's nothing in particular that I think I need to talk about right now. Okay. Let's do a quick recap. I just put this picture in here because I think this guy's the funniest guy in the world. So, recap of what linked lists are. You have a node, and the node has a pointer in it. And that node, the pointer inside the node aims at another node that is the same type as the one that we have. So if we do that, we will then have the ability to chain these identical nodes together to put them into a linked list. People are laughing. Yeah, if anyone hasn't seen this guy, this guy's the pineapple pen guy, and he's possibly the best dancer in the world. I have a node. I have a pointer. Pointer, node, node, pointer, node. None of those things. Linked list node. Okay, let's move on before I start performing the entire song. And this is roughly what a linked list looks like. Catherine is asking if the pointer has to be the same type of struct. If you are going to link a series of these together, then yeah, you want the pointer to point at the same type of struct so you can have another one of the same. It doesn't have to be the same, though. There are ways to join a series of things together that are all different from each other. But that's more specific. And that would involve us having to declare several different structs of different types. So we're not worried about that yet, because that's, I think, at the moment needlessly complex for what we're trying to learn. So what we're trying to learn is the idea that if we have a series of nodes here joined together by pointers, what can we then do with that? So we have a structure that allows us to build a list, and it's a list of identical objects, and then we're going to look at how we work with it. Corey, at the moment, yes, node is the name of the struct. And you'll notice in the example that we worked in last week, and the one that we're going to continue working with, is that I have named the node in that example player rather than node. Oh, hello. Oh, you're squeaky. Someone's come to say hi. Yeah, so here, the word node here is something that we have chosen. So we chose that because that's just the generic name for this. That's the name we're going to think of it as, except when we're using it for a specific purpose, we might give it a different name. So for the moment, node's just my name for it here. And I'm going to use it in a lot of the theoretical examples that don't have a link to something that we're actually doing. But as we make nodes that are for a specific purpose, they're going to have their own names. So for example, we're doing a list of players in the demo today, the one that we started last week. So we called them players rather than nodes. I'm still going to refer to them as player nodes a fair bit, because like the node is the generic term for an item in a linked list. In the same way that we have elements in an array or fields inside a struct, we've got those words that we're going to use for things. Lots of love for Chicken in the chat. It's one of those days. I think she was sitting in the window before and warming herself up, so she's going to want to warm herself up on my lap for a bit, I think. Okay. We looked quickly at looping through a linked list, and this is very similar to what I said when we were working with arrays. You know, so when I showed you an array the first time, it's like, hey, here's an array. Here's how we access individual elements into it, and then we move straight into how to loop through an array. So I think it's just as important as looping through an array is knowing how to loop through a linked list. So we want to be able to know how to take a pointer. So here we've got a pointer n that points at a list, and then we want to say, how do we do the simplest possible while loop to go through that list? So we take the pointer and we say if it isn't null. So if it's null, it means we're already pointing at the end of the list, or if this is the first time we've started looking at the list, that means that the list was empty if n was null. So we can have an empty list with a null pointer. And so we say if it is not null, it means it has an element. If it has an element, we'll do something with that element. So here, this is a simple one that's just going to print out the data that's in the list. So this is using this node struct. So the data happens to be an integer, so it's printing out as an integer. And then we move on to the next node in the list. To move on to the next node in the list, what we're going to do is we're going to change the pointer. So the pointer was aimed at, say, this node, and for us to move on to the next node, I have to change what my pointer that's aiming at this node becomes. So n, instead of pointing at this node, now points at this node's next. So this is this line here. N now points at n's next. So what we do is we look into the node and say, okay, who's the one after you? We're going to point at them now, and then we replace n with that. So this is our ability to move the pointer along the list, and this is our check to see if we've hit the end of the list or not. And otherwise, it's a simple while loop. So what that means, it's going to go from each node to the next node until it reaches the end. Zuhair is asking about the different ways that equals might work. Remember, and this is always an interesting one, is that the equals here is not the same as a mathematical equals. So it does not say that both sides are the same. What it's saying is take whatever's on the right and put it in what's on the left. So the way that we like to think about equals is the technical term for it is an assignment. So it is to assign a value to an integer. So we've got a value that's created on this side and it gets assigned to this, did I say integer? Sorry, assign a value to a variable. So we take whatever value comes out of the right hand side and we put it in the variable that's on the left hand side. So this pointer here gets its address changed, so it gets where it's pointing at changed to whatever address gets created on this side. So it happens to use the pointer itself, and this is using it before this action happens. So before this action happens, we look at the n, find its next, and then replace the n with it. So it's a little bit confusing, I know, because it's all on one line. It's sort of a compressed piece of code, but you can think of it as like we figure out what this is and then we put it into this variable. Okay, let's go back to what we were looking at last week. This is the entire specification of what we were going to do. We're going to use a linked list to track players in a game. So this was our player tracker for a battle royale game, a game like Fortnite or PUBG, or I don't know how many other battle royale games there are now, but I'm sure there's heaps. The trick behind these games is you have a lot of players in the game, and then everyone gets knocked out eventually until there's only one person left. So what we're wanting to do is maintain a list of all the players who are currently in the game, and then remove people from the game one at a time until there's only one left. So we started by creating a list of players, and then we were able to print out all the players in the game. And anytime we want to be able to print out the players in the game, which is why we put that in a function, so that we can call it again and again and again without having to rewrite the code. We are also going to look at the potential for us to control the order of the list. So we're going to try inserting into the list in specific order. We're going to talk about insertion a bit today. And then as the game actually plays, we want to remove people one at a time from the list. And this is not trivial because we want to figure out who we're removing, which means we're going to want to be able to look through the list and try to find specific people. So we're going to look a little bit at that as well. I don't think we're going to get to that today. We're going to basically be on this dot point today, which is inserting into the list and inserting in particular positions in the list. Because where I left us last week, I'll hop over the code in a second, was the ability to add items only as the new head of the list, because there was no other way we could sort of manipulate our pointers at that point to be able to add anything to the other end of the list or anything like that. Okay, people are asking a little bit about the n next pointer. I think Dean's helping you out there, which is handy, so people are getting some information from that. Yay! Alright, whatever you said, Dean, that works really well, because obviously a whole lot of people are saying they get it now. Okay, so we've got our player nodes. I think this is a lot of recap from last time, so what I might do... Yes, creating... Oh, I think I had a example here that I didn't use last time, because I've been watching a whole lot of Dragon Ball recently. I've actually finished watching Dragon Ball and now onto Dragon Ball Z. So the characters might change this time from last time. Anyway, let's hop over to... Oh, the code that I haven't opened. I forgot to open it in advance. Okay, so what we are going to do is first we'll grab the code from our lecture 12 and we'll copy into our lecture 13 directory. So I'm going to leave that my final state in lecture 12 as it was. So I'll make a new directory for lecture 13, and then I will copy lecture 12. Is it called Battle Royale? Yes. To lecture 13. I'll go to lecture 13, check that out. Yes, it's there. tab completing a lot here. I use tab complete a lot when I'm working in the terminal. It just speeds up what I'm doing, and it also means that I'm much more immune to typing in file names wrong if I just tab complete them. People are trying to figure out what games I play. I don't know if anyone came along to the crossover event. Daniel Mansfield and I did a stream together last Friday evening. We had a bit of fun with that, and we were talking about maybe playing some games next time. So we'll see if we can hook up something like that. Okay, so here's our code. Oh, I think we just had Dean was there at the time, so it was Chicken, and then myself and Dean. Because I think last time I did this, Chicken wasn't quite as much of an internet celebrity as she is now. But yeah. So we have our node structure, but it's not called a node this time. It's called a player because it's specifically going to be for the players in the game. So I would avoid naming my structs node unless it was a super generic thing that I was building and I didn't know what it represented. If I know what it represents, then I'm much more likely to give it the name of what it actually represents, so it's easier for us to remember what's going on with it. Each player has a name, which is a string character array, and each player also has a pointer to another player. So every player can be put into a list of players. We had a create player function, and it was pretty simple. All it was doing was allocating memory to a player pointer. So we create a player pointer here, so that's the variable type. Struct player pointer is the variable type, and it's called P. It's called P in this one because there's no particular meaning for this variable, because it's actually a temporary variable that's only going to be used to populate this player until we give that pointer back to whatever function called it, like this one here. So this one here is calling that function and saying, okay, we're going to start a new list. So every list must have the head of the list, which is a pointer that is aimed at the first element of the list. Sometimes this is null, so if the list hasn't been created and has nothing in it, we could call that null. But for the moment, what we're going to do is create that as the first element of the list. So in this particular one, we made Chicken the first player in the game, and we do that by creating player. Create player is going to give us back, and we know this because the function itself has an output of a player pointer. So remember, every function has a type. Don't get confused by the fact that there isn't a space between the type and the function. This is just the syntax for how we declare pointers. We put the star next to the variable name, but this entire section here is the type of the variable. So create player gives us back a player pointer. The player pointer it gives us back is pointed at allocated memory. So we do want to remember this thing that I've created here is creating memory leaks. I have not completed this to the point of cleaning up memory. Actually, I think I'm not going to clean up the memory until next lecture even. We're actually just going to keep building on this fragile house of cards that eats memory for the moment until we've gotten to a certain stage where we want to clean up memory. Okay, so we allocate memory, and then we know where that allocated memory is because we store the result of the memory allocation in a player pointer. So malloc is always going to give us back the memory location that it found memory for us. It will sometimes return a null, but chances are, if there has been an error in memory allocation, it usually means your whole program has stopped by that point. So if you really want to, you can check whether this is null or not to see if the memory allocation has worked. I even do that in the slides, but I've stopped doing it in the demos because I know that if this memory allocation doesn't work, the whole program's going to die right here. It's going to get killed. Remember when we intentionally used up 8 gigabytes of memory by creating a memory leak that happened in an infinite loop. That's the same thing that would happen if we try to memory allocate and we don't have memory available. Okay, once we have allocated memory, we will then fill out the fields inside the struct. So allocating memory is a little bit similar to if I just declare a variable. So if I was to, instead of that allocation line, I was to say struct player P like this, this would be the declaration of a new variable with no information in it. This is also, you can also think of this as the declaration of a new variable with no information in it, except the variable does not have a name. It only has a pointer that aims at it, and it is sitting in allocated memory somewhere. As opposed to this one, which is not in allocated memory, it is inside these curly brackets. It exists as a variable. So the difference between these two things, the key difference between these two things, allocated memory does not get cleaned up inside the curly brackets. So once these curly brackets close, this allocated memory stays. It's still available for us to use. Whereas this variable, if we had created this variable, this would automatically get destroyed. I mean, is destroyed the right word? Basically, yeah, I think it's basically the right word. It would get cleaned up when these curly brackets close. So if we want to have something that's created in this function that lasts longer, then we use memory allocation. Because there's not much point me creating a player that only lasts as long as the create player function. Once I've created the player, I want it to go into this list, and I want that player to still be around afterwards so I can keep using it. So that's why I would not use the normal declaration of a variable. I use a pointer to allocated memory, which lasts longer. It persists beyond the function that is in. Okay, so after we've created it, we then go through the fields here that are inside the struct, and we say for this individual player. So remember, the struct is the idea of a variable. It is not actually a variable. This declaration here does not create a variable. It creates a variable type that we can then use. This line here creates one struct player. So it creates one struct player in memory somewhere and maintains a pointer to it. So this is the same as somewhere in C, the idea of an integer being created. The idea of an integer is this is something that stores a number, and in most implementations of C, it's 32 bits worth of information. This is me saying, okay, I'm going to make my own one. It's a custom one. It's called struct player. It has a pointer to another one of its own type, and it stores a name that is 100 characters long. I'll let C figure out for me exactly how much memory that takes up, and I won't have to deal with how much memory that takes up because sizeof is going to tell me. So sizeof says, okay, this is how much memory that takes up. malloc says, cool, I'll give you that much memory, and then you can use it the same way you'd use a variable. So then I go into the variable and I say, okay, fields in the struct, let's populate them. So by the end of these 3 lines, I have an allocated piece of memory that is filled out with the name and next that I want it to have, and that really depends on what I tell this function to do. So I keep this nice and open, so the create player function can be used in a lot of different things that I'm going to be doing afterwards. And so when I'm finished with that, I've built the entire variable, it's ready for use. I give back the pointer, which means that whatever called this, so my main here, for example, calls this, needs to make sure that whatever is the result of the function that creates it, I'm going to keep that pointer. So the first one I'm storing in head, and the second one and third one are they're all getting stored in head, which is interesting because what they're actually doing is they're inserting themselves at the beginning of the list and pushing the others along, but they're still linking to them, because when I get added to the list, I then point at the old head, which is this one here that points at chicken, and then after that I replace the head with my own location. So the insertion, looks a little bit like this. So let's say, for example, I happen to be the first one here. A new person is created. So that's here. A new one is created. And its next is a copy of head. We can see that here because we put head in for input next. So that means that when this one is created, it will have its next pointer aimed at the first one, which is what's happening here. So after we create it, it's going to look like this. But then after that, create players output is going to be the address of this new one that's been created, and we move the head to aim at the new player by doing this. Head equals the output of create player. So this might look simple in terms of it just being this one little line of code, but what's going on is actually a little bit more complex, right? So when we create the new one, we make the new one a copy of the new one's next pointer, a copy of what used to be the head here. So they're both aimed at the same thing. That's two pointers that are a copy of each other means that they will both be aimed at the same object. So I've copied the address of this object here. The next thing I do is I assign the head. So it's nearly like what I do is I do this thing first, and then I do this thing. Because that's actually how C is going to work. It's going to say, oh, if you wanted to put something into this variable, you need to finish this thing first to figure out what you're going to put into that variable. So me doing this is me using the old version of head, and then I move head by giving head a new value, which is a new address. So now the head of the list points at me, and I point at what was the rest of the list, which is what the old head had been. So it's a little bit to wrap your head around, but once you get the idea of it, I think the key thing to think about here is how we are able to move pointers around by giving them new addresses. So we've done that here, where we had a current, which was a pointer to the start of the player list, and this was the same as the n next. So this is us moving a pointer, and it's always the pointer gets set to a new address. So moving it to the next is saying change the current's address to current next, and that moves it along. And this one has a similar thing happening where change where head is pointing and now point head at this new one. A little more detail as well, because the new one is also linking itself up with the rest of the list that's already been created. I'm just looking at the questions in there. I think Dean is covering all the details that people are asking. Yeah, I'm gonna let Dean answer those questions because there's a lot of stuff going on there. I know there's a lot of thinking going on there. There's a reason actually why we're 45 minutes into this lecture and I haven't introduced any new information, because what I really want to do is try to make sure everyone's got the fundamentals of what's going on here, which is why I'm repeating what we did last week, because it's this is the point I think where the most confusion happens in this course, and so I really want to get people the idea of like changing a pointer here. So head is a pointer because we know that it was declared as a pointer. But what I'm doing here is I'm not doing star head. If I was doing the star, that would mean that I was going to the node itself and changing the node. I'm not changing the node, I'm changing the pointer. So I'm changing the pointer itself. That means I'm changing where it aims, because the only thing that a pointer stores is a memory address somewhere in memory. So if I was to change a pointer, what I'm doing is I'm changing what memory address that pointer aims at. So that's what's happening here when I say the pointer then becomes something else. So the pointer becoming something else is the pointer changing what it's looking at. So there's all these nodes in memory, and I change where the head node aims by changing its value. Okay. Hopefully that's enough information that people are starting to get it. Then we were printing out the list of players where we were looping through, starting with the pointer to the head of the list. So we assume that we were given a pointer to the list itself. I created a new one here. You wouldn't actually have to create a new one because we know that this pointer is created in this function and it's a copy of, at the point here, it's a copy of the head pointer. So it would be safe for me to just move this pointer through the list, but I created a new one because a lot of the time when we're doing this, we're going to want to create a new one. I just wanted to show you doing that. So the current pointer is a copy of the player list pointer. So if this is called when we're given the head of the list here, current will be pointed at the head of the list. If current isn't null, what we were going to do is take the current name and print that out, and then a new line on the end of that, and then we were going to move on to the next element in the list. So current equals current next is me just saying, okay, move on to the next one. So I think I've talked about that a bit now. Hopefully that's starting to sink in a little bit, that me saying a pointer is equal to something different means it's moving that pointer to something else. It's moving the pointer to aim at something else. This function then is going to be able to, especially with this while loop through the linked list one at a time, stopping when its pointer moves off the linked list and goes to the end of the list. So did I? No. I know I have a diagram of that pointer moving along. That's in last week's lecture slides, so you can check that out if you want to. I think at this point I was going to go into a break, but we're a little bit early for a break, so what I'm going to do is at least spend 10 minutes more looking at inserting nodes into a list, at least the theory of it, and then we'll continue on from there. There's a lot of questions in there. There's a question about freeing linked lists. We are going to go through freeing linked lists. Don't worry if you can't free a linked list yet. It is fiddly. So I've got a whole section. We're going to spend time on that with diagrams and stuff like that. So don't worry if you don't know that. So at the moment, all we know is how to create a list by making new elements, the head of the list, and then the rest of the list is the tail of the list. And we know how to create a single node. So the next thing we're going to look at is how to insert nodes into a linked list. Okay, lots of questions there. I won't worry about the questions just yet. I'm going to let Dean cover all those questions. And Dean, you can ping me if you think that that I need to go over things again in terms of like lecture content and things like that. I mean, chances are I have a feeling that, like, I'll check on YouTube, I have a feeling that this series of linked list lectures is going to be the one that gets rewatched the most because it's got a lot of fiddly stuff. Okay, inserting into a linked list. We're going to look at the idea now that we don't just insert at the front of the list, but we can insert anywhere in the list. So this is the idea that we can squeeze nodes in between other nodes. I've got some text here that says how this is going to work, how we're going to move our pointers around, but I'm not even going to talk about the text that's on this slide because I've got some diagrams that show you how this works. We're going to go through that first, and this is going to be like, if you're really, really sure about what you're doing, you can just remember this via what's on this slide. But basically what we're going to do is we're going to change where a few pointers aim, and that's all we're going to need to do. Or we're going to need to memory allocate a node, but then all we're going to do is move a few pointers around, and we're going to end up with a linked list that has a node squeezed in between other nodes in it. So here's a really, really simple example. So this is an example of us only having 2 nodes in a linked list, but instead of replacing the first node as a head, so what we'd been doing previously was we'd been creating a node that would have appeared somewhere, and then it would have pointed at the head, as the first node will point at the second node. But now this time we're going to try to put a node in between these two. So I've left some space for myself in the diagram here, so I can put a node in between these. The first thing I'm going to do if I want to insert a node into a list is obviously I need to create that node. So I've got a new node here. It's made, but it's not connected, as in I haven't connected its next pointer up yet, and I haven't connected anything to it yet. So what we have here is we still have a legal linked list. So we can see that it's a legal linked list because we've got a head pointer pointed at a node, and then every node here is connected to another node until the very end of the list, where the next pointer from the node aims at null. I've also created a new node. It's not yet connected. What I'll do when I'm creating the node is I will take the next pointer of the new node that I've just created, and I'll say you should point at the node after you. So when we're going to try to insert a node in between two nodes, I should know which node is before me in the list and which node's after me in the list, so I can connect things up. So what I've done is I found a place between the first and second node where I want this new node to be. So if this node is going to end up between the first and second node, then its next pointer should point at the second node. I probably should have put a different number in this one, but we'll just leave it as it is for now. We're not really worried about the data that's in these, we're worried about the fact that we're joining them together. Hello. Someone's come to help me with the complex explanations. Okay, so the new node that I've created is now connected to the second node. I still, for the moment, have a complete working linked list here. So even if I have another pointer aimed at the second node, that doesn't stop this from being a working linked list. The new node is still not connected to this linked list. So we do have the three nodes, but they're not fully connected up into being a single linked list yet. And the reason for that is the first node next is still pointed at this second node here, not the new node. So because this is skipping this node, it's not yet part of the list. But because there's no way to access this node at the moment using the list and its pointers. So what I can do now, because I've got the new node is connected up to the second node, what I need to do is change this pointer. If I change the first node's pointer to aim at this node, like so, I set first node's next to the address of this new node. Now I have a head pointer pointed at a node. Its next pointer is pointed at a new node here. Its next pointer is pointed at this node here, which is another node in the list, and its next pointer is pointed at null. I have a functioning linked list now, but the difference is before, where I had only two nodes, the first node and the second node, now I have three nodes, and I've successfully inserted a node in between these two. And I left this like this on purpose, this awkwardness of the memory not being all lined up, because linked list memory is very, very rarely. Like, it's only by random chance is this ever going to be lined up in memory. Usually linked list nodes are just in random places in memory, and we trust the pointers to be able to find them when they bounce around between them. Oh, Mason is asking what the number in the highlighted yellow box means. That's just the data. So I could have these, if I wanted to, I could have these as names as well. I could have these as like Chicken and Mark and Dean, for example. That's just the information that they're carrying. We're not too worried about the information they're carrying in this because we're looking at the structures of how we put them together. Okay. There's code here. We're not going to do the code now because we're like 9:56, so I think we should go on a break. I've got a break slide here. I thought I'd leave you with a bit of homework. Probably not the best time for homework because I've just given you a new assignment as well. But I find a lot of this homework is quite interesting because there's a whole bunch of stuff out there in the world which is I don't know. It depends on how you look at it. Some people this is like super super interesting. Some people less so. But this is the kind of stuff that I think often inspires people to think about what they might want to do with computer science and things like that. So there's a couple of things that you can watch or read or play that are going to give you some interesting insights into computing. So AlphaGo is a really interesting one. So this is like one of the most recent, um, I guess you'd call it a breakthrough, a recent significant thing that computer science has done. I've actually got like a couple of friends who are in the background of one of the shots of of this movie, so it's pretty happy to be able to see that. So AlphaGo is done by Google DeepMind, which is a an institute working on deep learning AI. So this kind of the newest form of neural networks, and all the attached artificial intelligence that goes into using them. And it's about the program that plays the game of Go. And so very interesting. Much older stuff, but thinking about artificial intelligence and the philosophical ramifications of it. Some short stories by Isaac Asimov collected together in a series called I, Robot. Very very interesting. Um, it's fiction, but it has some interesting stuff to it. Neil Stevenson is also a brilliant author, much more recent because he's still active nowadays. Um, Two in particular, Snow Crash and the Cryptonomicon, are very very interesting novels. Cryptonomicon is a massive novel, but it traces the flow of research about cryptography. So this should be interesting to everyone who enjoyed the previous lab that was entirely about encoding and decoding information. The Cryptonomicon is like a fictional look at the historical period about cryptography. Computer science loves cryptography because that was the field under which modern computing was born. And it's not necessarily the only thing, obviously, not the only thing that computing does, but it was one of the first tasks that we succeeded at. So it's a nice thing to think about. I've talked about Human Resource Machine before. I love this game. It's on Steam, iOS, and Android, and it sneakily teaches you how to program in assembler. So you end up being able to write assembly code by the end of it, which is quite interesting. There's other things, there's board games as well. I particularly like this one called Space Alert, which involves you programming your characters to do something. I mean, there's less opportunity to play this now than normal because Space Alert's a board game where you kind of want at least 3 or 4 people to be together sitting around a table. And I think in the current, you know, climate of social distancing and things like that, we probably don't want to have our friends over right now. We probably want to play online games with them instead. But it's fun because what you do is you on in a physical board game you place sort of orders for your character instead of actually moving them. And then everyone reveals their orders together, and you figure out whether the stuff you programmed for your player to do is actually going to succeed or not. So, interesting little games like that. Okay, so let's go on break. It's exactly 10 a.m. now, so we'll come back at 5 past 10, and then we're gonna go deep into code, and we're gonna do insertion into linked lists, and we're gonna look at an attempt to do some ordered insertion into linked lists with some simple sort of alphabetical ordering. All right, be back soon. Oh, you couldn't see it. Chicken's been sitting right there the whole time, just sitting on my keyboard. Alright, back soon. I'm gonna hop back in because people are talking about marks, and there's a whole lot of like measuring going on right now. I'm not gonna say what it's measuring of because I'm not supposed to say words like that in a lecture. But remember that your marks are largely irrelevant compared to what learning you're getting out of these things. So I've seen people who failed the first assignment maybe scrape through on the second assignment and the exam and things like that, become quite happy and competent computer scientists. So please don't measure the marks that you get in your very, very first computing assignment as indicative of your potential for success in the future as a computer scientist. It's really not what that's about. It's just letting you know where you are right now. And I think I want to remind everyone, and if you need to, please go back and watch the professionalism lecture, which is the second bonus that I did in week 6, because I talk a lot about what it actually means to be a fulfilled professional computer scientist, which is very, very different from what it means to get really high marks in coding assessments. They're not the same thing. So it is nice to get high marks in things, but it's much better to be learning a lot and to be working towards your own goals of what you want to do. So just be careful of measuring too much with numbers. I mean, I know I'm fighting a losing battle here because I'm saying to a lot of students where a lot of the feedback that you're getting from us as the university and as your teachers and things is really, really specifically boiled down to just the numbers, just the marks, and I'm trying to tell you that they're not as important as what you learn about what you want to do in the courses. But I understand that message is really hard to push through while we're all working within this system that's all based on numbers. So for example, if I wanted to, I could judge my capability as a lecturer based on how much money they're willing to pay me. And that's really weird and different because, like, that would have me in a situation where I think, oh, because I'm a reasonably junior lecturer, that means I'm less valuable than the other lecturers, which is not something that I think my supervisors or anyone who works with me wants me to think, So that's not how the world works, and it's not the way that we want things to work. I want you to think about, because I'm sure there's people here who are not talking about their marks, and there's people watching who are not talking about their marks because they're like, holy crap, there's a couple of people in here who are talking about getting nearly high marks and complaining. And I just want to say a message to all those people that are there just going, oh god, are we supposed to get the same marks as these people? No, at no point do you want to need to get the same marks as the people that are getting nearly 100% of the course, the people who are talking more in chat, that kind of thing. It's more important you figure out what you're learning yourself, and if you think you learned something new in the assignment, and if you think you got something out of this that's going to give you more understanding of computer science in general, then that's good. That's where we want to be. We don't want to be measuring our marks and saying our uni marks are a measure of our quality as a human being. Like, I don't want anyone to ever sort of fall into that misconception that your marks are what makes you important or anything like that, And I should remind everyone that a mark of 50%, a pass in this course, is what I have deemed, and I hope you trust me in the way I've built this course, is what I've deemed necessary for you to be able to continue and to happily complete a degree as a computer scientist. It's a mark of 50. It's not a mark of like 85 or anything like that. A mark of 85, which is a high distinction, says you've gone above and beyond what was necessary for this course, and you have probably shown off the fact that you've done programming before and you could reapply it to this. And it's not necessarily indicative of Like, see, I could see heaps of people who would get HDs in this course who will not make it through a computing degree. Because that's not what gets you through the degree in the end. What gets you through the degree is whether you're actually interested in it or not. There's plenty of people out there who are just sort of good at everything that they do, but they're not necessarily interested in everything, so they'll get bored and they'll move on and do something else. So, I don't know. Again, it's a losing battle, but I'm going to keep trying to say this kind of thing. Your marks don't make you. They're not who you are. They're often indicative of where you are at a certain point in time. They're indicative of the circumstances around you. So, for example, I could have a student who gets HDs in everything. They're super smart and they smash everything. And then, like, one term they break up with their partner. And then, then they barely pass things and they fail a few things because their emotional state is at a point where it's very difficult for them to have their usual level of focus. And that doesn't mean that that person is suddenly bad at university. It just means that the circumstances around them cause them to think differently at that point in time. So your marks don't give you your value as a human being, and I really don't want people to be focusing too much on that. I'm happy for people to talk about the assignment and go, oh, this is what was cool about it, and this is what I learned from it, and things, rather than this is the score that I got at the end. But I do understand that everyone's going to talk about it anyway. But I want, even if you're all just going to talk about marks all the time, I want in the back of your head, I want you to think about the marks give me an idea of where I am, but they do not give you a ranking between yourself and other people. Don't ever get caught up in that. Competing between yourself and other students usually leads to a negative mindset, which then ends up because if you just want to beat everyone else, you can strategically work your way around to the fact that if you can just sabotage everyone else, then you will win in a competition. As opposed to a better way in education is like, have I learned the most that I possibly could? And have I improved on my previous learning? And that doesn't mean have my marks increased. Like, don't get stuck in that kind of weird progression curve, because that's impossible. But am I happier with my learning? And that's the thing that you want to work on. Anyway, I just wanted to talk about all that because I saw the way that the conversation was going in chat, and I really wanted to try to shift that conversation. This is a constant struggle for me, right? I know I have to go back to lecturing, but this is a constant struggle for me, is that I see students, and I see the majority of students who've just done their HSC. And I know that the HSC is entirely based on reducing human beings to a number out of 100. And I think that's one of the major failings of our educational system, is that we reduce humans to numbers. I think it would be really interesting if at the end of the HSC you have an interview with a teacher who has spent a significant amount of time with you over that year, and they talk to you about the things that you've progressed on and how your attitude towards learning may have changed over the year, and then you'll actually get something out of that, as opposed to you are a 95 and that person over there is a 65, therefore you have more value to society than them, which is complete fucking bullshit. Anyway, let's move on, because I think we need to actually talk about talk about some programming, because otherwise you're going to be with me all day, and I'm going to talk about how I would prefer you to be educated than how you have been educated. But I'm hoping that this message that I say to you sticks in your head and potentially continues onwards through your education, and learn to take a lot of the formal side of education with a grain of salt, because a lot of it is just there because of the structure of the environment and not what you need for your learning. and what you need is always going to be based on where you're trying to end up. All right, let's not go. Okay, I've already spoke about this for hours with Dan Mansfield the other night. I didn't save the videos, like from those casual live streams. I don't save them because I want my YouTube channel to only be on subject content. But maybe at some point I'll start a different channel that's more casual and actually saves those videos. But anyway, all right, let's actually move on. Okay, so I talked about inserting nodes into a linked list, and here was my my diagrams for doing it. Is I'm going to create a new one. I'm going to link its next node up, and then I'm going to connect the first node to that node. And the code here is like this. The code is deceptively simple. So let's go across. Like this is this point that you reach, and certain things in computer science are always going to end up like this, where you do a lot of thinking. A friend of mine told me this story of Hapkido or Aikido. I can't remember which of the two Korean martial arts it is. And he talked about this monk that went up this mountainside and fasted and meditated for 20 days. So they didn't eat for 20 days. They just meditated. And he came down the mountainside and he said, I have invented a new weapon, and it's a 3/4 length staff. So they're using staves that were taller themselves, and then he invented a staff that was only about shoulder height, which means you could use it like it was a sword, or you could use it like it was a staff, and that was like a revolution in weapon design. It was just a shorter staff. But he went up the mountainside, 20 days worth of meditation and thinking about fighting forms, to come back with a really, really simple response to the way other people were fighting and things. And I don't want to belittle that response, because even though it was simple, you couldn't think of it unless you had done all of that thinking. So you couldn't create it without all that thinking. And this is what we're doing here. It is literally like 4 lines of functional code. And actually it's an if-else, which means that it's actually just 2 lines of functional code here, but it requires a great deal of thinking to understand just those 2 lines of code. So let's go across and make those 2 lines of code. So I am going to make this a function called insert player. And in order to insert a player, it's going to need the information about the player, which is going to be the player's name. I'm going to use the same kind of naming scheme I had here, called input name. And I'm expecting this array to be of max name length. So I've got here insert name. Oh, I also need to know where I'm inserting it in the list. And I'm going to call that insert pos for insert position. And I'm also going to return a player pointer. And I'll show you why I'm returning something from this. Because there is an example of me inserting something that is going to need to change what the head of the list is. So I will return, and it's going to feel a bit weird, but I'll show you what it is I'm actually going to return the point that I've inserted the item at. This means that if I insert an item into an empty list, instead of returning and having that list still be empty, I'm going to return back the pointer to what I've inserted. Let me do the actual code, and then I'll show you how that works. All right. So here we have the function itself, and I'm going to put my comments here, saying insert a player into a list as the next node after insert position, maintaining the list as it was. Oh, it's not really as it was. Maintaining the rest of the... Actually, I don't really need to say that. I'm going to say insert into a list. I was trying to explain that this was not going to remove anything from the list. Actually, maybe I should just say that. This will not remove any elements from the list. And it returns a pointer to the inserted node? Are we returning a pointer to the inserted node? Not necessarily. But maybe we should return a pointer to the inserted node. You know what I'm going to do? I'm going to leave this blank until we decide exactly what we want to do with that. I know one of the situations that I want to do something with, but I do want to actually like step through what's happening here before I decide exactly how that's going to go. We're getting to this point of the term now where I'm actually just going to make decisions about what we do as we write the code. And I'm going to talk through, I think it's important that I talk through my decision-making process on these things, because a lot of what I'm demoing here, it's actually not super relevant what I write here in the code. What's relevant to you into learning about using linked lists is like, what am I actually thinking about when I'm doing this? Okay, so let's take the example that we had here, and we say, okay, so if I've got two nodes, and I know that insert position is the pointer to the first node, and I want to insert something in between those two, what do I do to do that insertion? So the first thing that I definitely want to do is create a player. So I know that I have to do create player. If I'm going to call the create player function, I definitely need to keep track of what pointer it gives back, because it's going to give me a pointer to the thing it's just created. So let's make a player pointer, and we'll call that new player is equal to create player. Create player needs certain inputs to work, so it needs an input name, and we've got an input name here. So we'll put the input name in, and then what we'll do is we will say it needs a next pointer. So if I'm in this situation here where my insert position is pointing at the first node, and I want the next pointer to point at the second node, that's cool because I've got this here. So I can say my insert position's next pointer is the thing I want to copy for my own next pointer, which takes us to this step here. So this pointer is a copy of this pointer. We know that's a copy of that because they're both pointed at the same object. So my new player is create player here, and it is insert pos next will become its next pointer. So this will then create a new player. This will take us to this position here, where the new player is created and its next pointer is a copy of the insert position's next pointer. The next thing that we were doing is we were taking the next pointer of the first node, and then we were aiming it at this node, which is this step here. So we take the insert position's next pointer and we aim it at the node we've just created. So we say insert position's next pointer is now going to become the location of this new player, which is actually just that pointer. So that's actually it. It's not completely it. We still have some issues here. But what I've actually done here with just these two lines of code is this entire sequence. So, see what we did here. We created a new one. Yes, we created a new one. In creating the new one, we gave it the name that we were given. So if I say insert player and the name is Tom, for example, then it will put that name in. And then I said the next of the thing that we've just created is a copy of the insert positions next, which is this part here. So a copy of the first nodes here's next. So this is the insert position is the one just before where we're inserting. And so this was the creation of the node, copy of the next pointer. It has whatever data that's in it that it was given. I don't know when I'm making this function, obviously, what the data is going to be. And then the next line says, take the next pointer of the insert position, so that's the node in the list that's before the one that we're inserting, and aim that at the new player. Like so. So, if we have this situation, where we have a node before and a node after, this is enough code to make that work. And it's a really, really short function, but this will do what we need to do for most situations. And I say most situations because I can already think of some situations where this is not going to work. So, let's start thinking about this in comments. Insert after a node that exists. There is a chance that I could get insert player called on a list that doesn't have any elements in it yet. So if the list doesn't have any elements in it yet, then I am going to get a null as this input. So I'm going to get a null pointer, and it says, can you insert into this empty list? And it's like, well, sure, of course I can insert into an empty list. That's easy. Because then I would just create a new list that has only that node in it. So this is going to insert after a node that exists, but we also need to insert into an empty list, which is going to be different. We also potentially have other issues that we might need to think about. What if we wanted to insert at the very end of a list? So what if our insert position is the final element of the list, and we're trying to insert after that? Is that something that we can do with this code? So let's have a look at this code and see if that will still work. So if I create a new player and I have the name, that's no big deal. Insert position next. If insert position next is null, is this still going to work? So this is the example of what if this was the insert position and I'm trying to add something after the end of the list. Does my insert code still work? So insert position next is null. Is there anything in create player that stops me from putting null, the input next, if that's null? No, that's fine. And then insert position next, which was null, now becomes a new player. Cool. Alright, having a quick look at that, I can see that inserting at the end of the list will still work. So I still need to think about inserting into an empty list, or potentially... Actually, no, I was thinking about what happens if we try to insert at the start of a list, but we can't actually insert at the start of a list because we've said that we're going to get an insert position which is aimed at a node in the list, and we're inserting after that. So if we were going to insert at the start of the list, we could probably use our old code that just replaces the head of the list. So for the moment, that's not going to be in this function. But we still need to think about what happens if we insert into an empty list. So if we're inserting into an empty list, we need to check whether that's going to happen or not. So let's say if the insert position is null, then I'm inserting into an empty list. So then what I need to do is I need to create the player and probably I'm going to give back the player's a pointer to the player itself, because the insert position is null. I don't want to give back null after I've created something, because that will actually mean that I've lost that piece of memory. So then I would give back a pointer to the player itself. So I think that we're going to be returning a pointer to the inserted node. We'll see if that still is the case afterwards. Okay. So I've got two ways of inserting here. I think that this one's going to be in an else, because I only want to do one or the other. Right, so either I'm inserting into a list that's empty, or I'm inserting to a list that exists. For all the cases of inserting into a list that exists, I'm going to be using this code. If I'm inserting into an empty list, I'm going to use a special different bit of code. What I think I'm going to do is create player outside of this here, so that I only do it once, but I know that no matter what happens, I've created the new player. Note that I cannot necessarily do this, because I can't access the next of insert position if I don't know that it's not null. So if insert position happened to be null and I said insert position next, I would get an issue saying that I tried to access a field inside a null pointer. So you may have seen this if you tried to access structs via pointers and you haven't actually got a pointer to a struct. If you have a pointer to null and you try to access the field, you get a null pointer exception. So what I'm going to say is, for starters, I'm not going to set up the next pointer, and that's going to start to look a bit more like this, where when we create it, the next pointer is not pointed at anything yet, and then we'll set it to this only if we need to. Okay, so create player now is making a simpler node that doesn't have any pointers coming off it. So if it is pointed at null, then it's saying there's nothing after me in the list, which means if I'm creating a new list, what I can do then, I wonder if I did it this way in the code. Nope. I was doing something different in the code. Let's see if I end up doing that later. But what I think is going to happen here is if insert position is equal to null, I actually don't have to do anything, because I've created the new player and I've said that their next is null, which means they're already the start and end of the list. So I may not even need this if statement here. So I'm going to leave this blank for the moment, because it actually doesn't need anything. And I'm going to say if we're inserting after a node that exists, I am going to make sure that this next pointer points at the new player, which is here. And thinking about it, I don't need to do anything else, because I have created the player with the right name. Insert position next is new player. Oh, no, wait. I need new players next to link up first. So first thing I need to do is new players next, which is this bit here. I need to take new players next and make that the next of the insert position. So the insert position's next. Okay, so this thing links the newly created node with the one after it, and this line here takes the node before it and links it up to the new player. So this is saying after the new one that I'm inserting is what was next in the list already, and then what's after the position that we had then aims at our new player. Noting that this if statement here is empty, I should be able to flick these around, so that what I'm going to do is get rid of this entirely and say if the insert position was not null, then we do all of this. If the insert position was null, then we don't do anything, we just create this new player. So we're going to create this new player, and if the insert position exists, we do the insertion. Then we're going to return the player, the new player. So what this is going to do is, If the list was empty and we're inserting into an empty list, this is going to create a new list with only one element in it, and it's going to return the new list. If it did insert somewhere else into the list, it will insert somewhere else into the list, and it'll still just return a pointer to the new element that it inserted into the list. We may not necessarily use that in that case. Now I know why we do this. I think... Let's see how we go with this. I think this will be okay. So I think this, at the moment, we will be able to just use this like it is. But what we need to do is we need to test this under a few different situations and see whether this is working. So the functional code really is in here, saying in order to insert something, I create a new one and I say its next points at the one after that I'm inserting at. And then the one that I'm inserting after will then point at me. So basically these two lines, this line and these two lines, are doing this. So create the new one, make its next equal to this, and then make the next of the one that we're inserting after aim at it, and then we have a full linked list. The only other stuff I've done here, and I've done this convoluted chain of thinking that that we're going through here, was to get me to the point where I could also insert into an empty list, and it ended up with a kind of minimal amount of code anyway that says that if I'm going to create a new one and the list was empty, so if this if statement fails, we're still just going to give back a link to the thing that we've created, so that we don't necessarily have this memory allocation without a pointer to it. Let's see if we can get this stuff working by... We're going to remove all of this for the moment, and instead of what we had before, I'm going to make a new list that starts off empty. So this new list has nothing in it. Then I'm going to call insert player. Into this new list, and insert player takes the insert position. So I'm going to say insert after the head of the list. And this is going to be interesting because the head of the list is currently empty. And the first player is going to be chicken. So we'll put chicken into the list first. And so what we should get after this is that the list becomes a list with chicken in it. But because this head was null beforehand, I'm probably going to need to make head equal to the insert player. Let me just check if I was... Oh, right, okay. We did it a little bit more simply in this example here, where we just created a list with at least one player in it. I think we can do this way. So we're going to create a list with chicken in it. And then after that, we don't need to do this reassignment of head or anything. Head will remain that. And what I can do now is I can just do insert player, and I can say after the head, let's say I come after chicken, because I'm chasing her around the house all the time. So the first element of the list is going to be chicken, and because I have been inserted after the head, because we look at insert a player into the list as the next node after insert position. So if the head is insert position and I'm inserted afterwards, what I should be is now the second element of the list. And let's print out the list and see what we get out of that. So let's compile this. Actually, the first test is to see whether this thing actually compiles. Because I've written a bit of code. Well, actually, I haven't written very much code. I've done a lot of thinking. I've written a small amount of code. Okay, we've got that there. And then we'll run it. chicken and then mark. Okay, so did that link up with what I said was what I hoped would happen? So here I've tested whether we can insert into an empty list, which would be if this if statement doesn't run, and it looks like that worked because chicken is in the list. And then I've also tested after that, can I insert into the list after the head? So can I insert into the second element of the list? And I can do that. So I could insert here, and my name comes next. If I want to now, I can do some pretty funky stuff with this, where I can get a list that has a whole bunch of elements in it, and I could insert anywhere in this list. So I could say, go 5 elements into the list with a counter, and then insert after that, and I can squeeze nodes in between other nodes. Okay, so I think there's a lot of questions happening at the moment. Dean pinged me there. And said, let's remind ourselves of what create player does. So create player allocates the memory for a new node. So this is like creating the node itself. And then all it does is it takes whatever the input name was here and whatever the pointer input next is and puts those fields in and gives us back the address of what was allocated. So when I say create player here, what it's going to do is it's just going to make a new one with whatever inputs we've given it. So in this case, we're going to take the input name that we've got there, and we're going to take null. So we're going to say that the next pointer doesn't have any value yet when we create it on its own. So this is like it would be the last element of the list if it had null. However, if it's inserting into a list, so inserting after a node that exists, so if insert position is not null, then what we're going to get here is this is changing what the new player's next pointer is. So the one I've just created has a next pointer of null, but what we're going to do is say instead of making that null, we're going to make it a copy of the insert position's next pointer, which is here. So I've created it, and for the moment it's not aimed at anything, but this is my insert position. So this is the thing I'm inserting afterwards, and it has a next pointer that points here. So I make mine a copy of it. That's what this line of code is. So take the insert position, take its next pointer. Insert position's next pointer is aimed at this node. Then, when you've got that, assign that to the new player's next pointer. So new player, next pointer, then aims at the same thing that this pointer is, because this line has done that. We've grabbed the insert position's next pointer, and then we've made the new player's next pointer a copy of the insert position's next pointer. Then this next line says, new player. What is the address of new player? Address of new player is this location in memory. And I've said, take the insert position's next pointer. So insert position, next pointer, and make that now equal to this location in memory. So for this pointer to be equal to this location in memory, that means it is aiming there. So that's what this line does. So it says this location in memory, make this thing equal to that location in memory, which then leaves us with this fully connected linked list with a new node inserted into it. So as I was saying, right, a lot of thinking and very little code. So this only has 3 functional lines of code in it, but we had to do a whole lot of thinking to get ourselves to the point where we can understand this. We had to figure out that what we were doing here is moving pointers around. And that's all we're doing is changing where these 2 pointers aim. So these are the pointers we're altering, and these are the new locations we're going to aim them at. That's the way you can think of it when we're doing pointers with equals in between them. And that follows the movement of the pointers in this set of diagrams here. Okay. I think that hopefully people are starting to understand what's going on here. I fully understand this is a bit of a brain burn. This is always a bit of brain burn, but hopefully with the diagram and seeing how we can translate that diagram into this code, each of these lines of code is moving where a pointer aims. So it's changing where one of those arrows points in the diagram. So hopefully, with a bit of practice, you'll be able to link those up. And hopefully also your tutors are going to teach this week, and so you'll get another look at how this works via that. And hopefully, I think, because a lot of the tutors have learned this more recently, so they can just tell you, okay, this is where I got confused as well, and so this is how I can help you learn this. Okay, so now we have the ability. So if we move on from this, what we can move on from this by doing is saying, now we can assume that we can insert a node, a player, after another player. So this happens to be inserting after the head, but you could insert after other things if you want to. So we had a pointer to something else. We could say, okay, insert after this insertion point, which means we now have the ability to put a node or a player into the list in any location we want to, so long as we find a pointer to the location that we want to insert after. So if we want to, we could insert several people after the head and the list, and we can build this up. So I could insert a player. I could insert them after the head, or I could do something interesting like this. Actually, let's just insert after the head. Make it easier. Let's bring on Frankie. Frankie the Fox. So what I'm doing here with this is I'm creating a new list with nothing in it. And then I'm doing this special line, which is going to insert chicken into the head of the list and create the new list out of that. Then I'm going to insert Mark after the head of the list. So chicken's the first element in the list. I've inserted myself afterwards. And then I'm inserting Frankie after the head of the list. So this is actually squeezing Frankie in between myself and chicken. So this is like saying chicken's here, I'm here, Frankie goes in between because Frankie's getting inserted after the head, chicken's the head of the list. So what I should get is an interesting order when I print this out. So let's compile that. Because what I did is I had this list first, chicken, then Mark, and then I've inserted Frankie in between the two. So what I should see printed out here is chicken, then Frankie, then me, which shows you that now we have the ability to have a list that already exists and squeeze in elements in between them. People are asking me if I'm going to upload this. Yes, I'm definitely going to upload this. And yes, we'll have Daniel Mansfield as the fourth player if you want. Okay, so running a bit short of time, but the next thing I want to do is try to insert with some conditions. So what I want to do now is try to leverage comparisons on strings to do an alphabetical order insertion into the list. So if we're going to do an alphabetical insertion, we can use this function called COMP, which is short for string compare. String compare compares two strings and says 0 if they're equal, or negative if the first one has a lower ASCII value than the second one, or positive if the first one has a higher ASCII value than the second one. And we can use this to do alphabetical order. So I can say if the strcomp between two strings is positive, it means the second string is later in the alphabet than the first string. This is going to get confused by any other characters that might be the first letter. It's going to get confused by capital letters versus lowercase letters and things like that. So it's not perfect, but we're going to use it just as an example of how we might be able to decide between two strings whether something should be before or after something. So what I'm going to do now is loop through a list, looking for the point that I want to insert into the list. So every time we're going to loop, we're going to move through the list and find the position where something should be inserted based on alphabetical order. So we're going to loop through and we're going to say should I, for every element we look at, we're going to say, should I be before or after you in the alphabet? And then, depending on whether I'm before or after something in the alphabet, once I get to something that I should be before in the alphabet, I need to insert before it. If everything I look at I should be after it in the alphabet, that means I'm going to loop further along. So I'm going to keep looping until I find the point where alphabetically I should be inserted into the list. So it's going to look a little bit like this. So I'm attempting to insert a player with the name D into a list that's sorted. So I'm going to assume at this point that the list that I'm inserting into is already in alphabetical order, and I'm just going to add another letter here. So I've got the letter A, C, E, S. I don't know why I spelled out aces. I think I just started typing stuff and then it ended up like that. So I'm going to start here, and a loop is going to move a pointer through the list. So when I'm looking at the A, I compare D and the A. So this could be a longer string as well. I'm just going to trust string compare to do this thing for me. So I compare the D and the A, and I say, no, I should be after you because I'm D and you're A. So I move on to the next one, and I hit C, and I say, I'm D and you're C. I should be after you in the alphabet. And then I'm going to get here, and I'm going to see E, and I'm going to say, ooh, I should be before you in the alphabet, and so my loop stops. So I stop with one pointer here, and I know that I'm going to insert this D in between these two, because I've checked that I was meant to be after this one and I was meant to be before this one. And so if I'm meant to be after this one, before this one, I should be in between the two. So I'm going to insert D in between these two. Let's start the code for this. I know I've only got like 9 minutes left, which means I'm probably not going to get to finish this code right here. But what I'm going to do is try to loop through and find the point of insertion with string compare so that I can do a new function which is going to insert alphabetically into this list. So I think I am still going to return a pointer, because every time I work with a list, if I change the list, I probably want to return a pointer to the list. So I'm going to call this one insert alpha because it's alphabetical. And I'm going to take the head of the list, and then I'm going to take the name of the new thing that I'm going to create to put into that list. So let's take this function, and I'll create a new one here. And I want to explain to myself and whoever else is reading this, insert a player into a list in the correct alphabetical order position. This assumes that the list is already in alphabetical order. Because if it's not in alphabetical order, there's no way for us to insert into it in alphabetical order. Like, how do we know where, if the thing isn't already in order? So we're going to assume it's already in order. We're going to loop through, find the position that we need to be in, and then we're going to insert there. Returns a pointer to the head of the list. Okay. So this thing is going to give us back a pointer to the head of the list. It takes in a pointer to the head of the list, so it's not too hard to return that pointer unless it changes. So we'll have to look into that. Let's do this in terms of thinking about what we're going to do. So the first thing we're going to do is loop through the list. So this is that thing I do where I think in my comments first before I go deeper into things. Find the position that we want to insert into. What this is check for when we should be before something alphabetically. So if we're looping through a list and we see that we should be after something, that means we continue looping. If we see we should be after something, we continue looping. And then here we should see that we should be before something. And so if we should be before something, we should be inserting before it. But we should be inserting after any of the things we said we should be after. That's how we find the position we need to be in. Then insert at that position using our insert player function. These comments will allow me to piece together this function as we go. So I know that I'm looping through the list. I know that I don't necessarily want to change where the head pointer is, because the head pointer is the pointer at the start of the list, and I know that I want to return the head pointer, so I should have a copy of that. So let's make a new pointer called current, that is the current thing I'm looking at as I loop through the list, and we're going to start that off as the head pointer. So it's going to be pointed at the same thing that the head pointer is. It can move, the head pointer is going to stay pointing at the first element. So to find the position we want to insert into, we check for when we should be before something alphabetically. So it's quite specific about that. I probably don't need to have a comment, an actual comment saying loop through the list. So find that position. So we're going to loop through the list, and we know we're definitely going to stop looping if current was null. And in order to loop through the list, I need to, every time I iterate, I'm going to say current is going to move to its next pointer. So this is me moving the pointers through the list. So this is just the basic structure of moving through the list. I want the current pointer to stop when it reaches a node that is after where we should be. So this is this check. So actually, I'm not going to get rid of that comment yet. I'm going to use it. So what I'm actually doing with this loop, you know how a lot of the time when we make a loop, what we do is we want to do something to every element. So we go through every element, we do something to every element. This loop is a little different. This loop is just moving through a list, and what I want it to do is stop at a certain point. At a certain point, I want it to say, okay, this position in the list is significant to me. So what I'm actually going to edit here is not what's inside the loop, but what's in the stopping case. So what I'm going to say is stop at a certain point. So I want the loop to keep moving if my string is after this string in the list. And I want it to stop moving when my string is before this string in the list. So these are just letters for the moment, but in our example, they're actually strings. So I want to add another stopping case to this while loop, and I'm going to use the string compare function for that. So I said what the string compare function did: 0 if they equal, negative for one possibility, positive for the other. So I want to stop on one of these, and I'm just going to check which one that is. But first of all, what I'm going to say is I'm going to compare two strings. So the first string that I'm going to compare is the input name that I've been given. So the input name is the node, the name of the node, the name of the player that we want to insert into the list. And I'm going to compare that against the one that I'm currently looking at. So I've got a pointer that's moving through the list. So I'm going to say, look at the name of the node that I'm currently looking at. And so here's a string compare. And I need to say, is this going to be positive or negative? So if mine is the first one, Negative if the first has lower ASCII value than the second. I think that's what I want to stop under. So I want to keep going if the first has a higher ASCII value than the second. Yes. So what I'm saying is, this while loop will keep moving on to find a new place if I am later in the alphabet than the current name. But if I am the same or earlier in the alphabet than the current name, then this while loop stops. When this while loop stops, current will be aiming at the node after where I want to insert. So if it's aiming at the node after where I want to insert, I need to know this node before it, which is my insert position. I might make this a comment that's... Actually, you know what? I'll just leave that whole comment in there. So what I've done is I've got a pointer to current, and I'm looping, but the point at which I'm stopping is where I think that alphabetically I should be there. So I'm going to insert at that position, but I can't use current as the insert position, because current is actually the one after the insert position. What I want is the one before, and I can't actually go back and find the one before like this. So I'm going to use an interesting trick here. I think I'm just about to run out of time, but I'll just show you the trick. I'm going to move 2 pointers through the list. I'm going to have a current pointer and a previous pointer. I'm going to start the previous pointer as null, because if I'm at the head of the list, there is no element before me. So what I'm going to do is I'm going to move 2 pointers along. And the way I'm going to do that is kind of do this leapfrog thing, where I'm going to say, when I'm in the list, the previous pointer will point at the current, and then the current will move on. So that way what happens is when I finish an iteration, the current will be where I'm looking at the moment, and the previous will be where I looked at the previous iteration, which is why it's called previous. So I'm going to say previous is then equal to current. So 2 pointers. First one's pointed at the head. The previous is just off somewhere because it's pointed at null. Then when I go through the first time through the loop, previous is then pointed at the head, and then current moves one along. And then the next time I come in, previous moves to current, current moves to next. Previous moves to current, current moves to next. So what I'm actually doing is moving 2 pointers through the list, because the previous pointer is going to end up being our insertion pointer. Because we wanted to insert at the position, and what we were seeing was that this was ending here. I've gone a little bit over time here, so I think I'm going to have to pause this, but that's okay because we're going to continue this afterwards. But what we were going to do at this point is that we were going to insert at previous, so it's actually pretty simple. I'll show you. What we're going to do now is we're going to call insert player here, where the insert position is the previous pointer and the thing that we're inserting is input name. And then we're going to give back the head of the list. This doesn't do everything. This doesn't sort out the idea that we might be inserting at the very start of the list, but it will do all other situations. But I'm going to wrap it up there. On Thursday, we will come back to this, and we'll go through this again, and I'll show you how this works, and we'll do alphabetical insertion into the list. And we'll continue, and we're also going to do some removal from the list and actually have this game able to play. But for the moment, I will leave that there. Priya's asking why we return the head of the list. And I haven't actually shown you why we're going to return the head of the list. The reason why we're actually going to do that is because there is a chance that we would insert before the head of the list. Because if we're inserting alphabetically, for example, if I inserted Mark first, then chicken. Chicken would have to be the new head of the list, and I would get pushed back one. In which case, the pointer to the head of the list would change to something else. So it wouldn't just be returning back what we had before, it might move to something else. So that's why we would return the head of the list as something different if we inserted before the beginning. Yeah, you're right in thinking that we didn't change it in this case. Alright, I should wrap up there. People have probably got tutorials to go to and things like that. So what I'm going to do is I'll go into break mode or wrap up there, and I'll come back afterwards and I'll answer any questions people have on this. There's a lot of code here, but more than code, there's a lot of thinking that's gone on here. And I'm trying to cover everything, which is not necessarily going to cover everything at a full level of understanding for everyone. I'm just trying to cover all of the content so that you can actually go back and watch it later and things like that. Okay, so I'm going to go back into the break mode, and actually for everyone, because you probably wouldn't have noticed, there's a little bug that has been warming herself on my lap this whole time, just to say goodbye. And I will come back after break mode and answer any questions people have, but otherwise this is the end of the official lecture. Alrighty, I'm back. Okay, so let's see if there are any questions. I saw a couple of questions in chat. I was just resting my voice a bit. I realize that like the more difficult the content is, the more active I get in my speaking. It's like, okay, this is really full on, alright, so we're gonna get really deep. Michael's asking how much linked lists come up. And I think that Dean was answering that already, saying that like, yeah, this comes up a lot. So, but it depends on which kinds of fields in computer science you're working in. So a lot of the actually no, it doesn't anymore. It used to depend on which fields you're working in because the linked list thing and what it extends to are some of the core concepts in artificial intelligence. And that used to be something where it was like, okay, not everyone's going to work in artificial intelligence, but nowadays, like 60% of people are going to be working in artificial intelligence. So the answer is yeah, it's going to come up heaps. So the linked list is one node connecting to one node, connecting to one node, etc. But imagine if each node in the linked list had multiple pointers. So the most basic of these is every node connects to two nodes. Hang on. Let me just... So here's a linked list. Oops. Sorry. Ran out of mousepad space. But what if we had this? Etc. We would then not just have one list of items that we were looking through, we'd actually have choices. And every choice we make when we branch changes what our options are in the future. So that's one thing. And then another is this possibility where you can have more pointers to things that don't necessarily continue in one direction. They can go backwards. You can get this, which is an infinite loop of possibilities and things. And this is how we model nearly anything that's going to control something. When you consider it, this is a map of your code. So your code runs in what appears to be a straight line, except every time it calls a function, it might do something different. So this structure that we're building, the simplest structure is a linked list. It, with just a little bit of extra pointers, becomes immensely more complex. And you think about, like, we have a while loop to go through and look at every node in the list. If we think about what we need to do to look at every node in this list, it's much, much harder. And how do we know that we're not looking at the same node again that we've seen before? How do we know that we're not infinitely going back and forth between two, or that we haven't gone back to the beginning or anything like that? How do we find all of these endpoints? Oh, that's not even an endpoint because that one can go back. So this one and this one are endpoints, right? So this comes up in planning. It comes up definitely in artificial intelligence. It comes up, well, planning is kind of, to a certain extent AI, and it comes up in just data flow, just like the idea of what happens in what sequence and things like that. So this stuff here is full on. We're not going to talk about any of this stuff in COMP1511 because, as you've seen today, the mechanics of just using a normal linked list involve sort of melting your brain and forming it into a different shape and hoping it still works afterwards. But this is where it goes, and it's very, very important. I'll show you another structure that's pretty common. trying to not have to draw a million of these, but I still want it to be relevant. Stop me if you've seen this diagram before. This isn't fully linked because I can't be bothered. This is a neural network. You know those super famous things that everyone's using to make computers smarter than humans and a whole bunch of things? Each of these is a node. Each one has pointers to other nodes. Each one contains a certain amount of information about what's happening in this system. The inputs go in one side. Their numbers change how much information gets passed on these links to these other nodes, and eventually this output comes out here, which gives us an answer to a question. Oh, Echo, you'd seen it before, right? Yeah. So this structure is not that much different from the linked list. I mean, it's infinitely more complex because we've joined all of these things together, and we're talking about how data moves. So if I was going to put arrowheads on all of these, they are all directional, as in it goes like this and like this. The data moves only from one side to the other, or from your perspective, from one side to the other. I just realized my face was covering some of that diagram, but anyway, it's fine. Yeah, the structure of nodes and pointers, it's not always going to be pointers. Sometimes these links are actually structs on their own, because what they do is they actually modify the data as it moves between the nodes. So this is a struct, this is a struct, this is a struct. So it's even more full on than what we're doing. But you're learning the basic concepts that could build up eventually to being able to build a neural network. Give it some time, though. I think that wanting to build a neural network now is very, very cool, and it is even possible. But if you want to get the strong grounding and understanding of these, we want to work our way up through these first, and then we'll get to this complexity of structure. So the linked list, this is how the linked list builds. Because you can see there's no specific reason in the struct of a linked list why it only has one pointer. You know, I could have an array of pointers, or even bigger brain, I can have a linked list of pointers inside a linked list node. And then you can get these kinds of epic structures like this and this out of that, or an optional number of arrows coming out of it, you know, that kind of thing. Okay, hopefully, Michael, that answers your question. So I think it's a good question, though, because like I've had several jobs. One of the jobs did not use linked lists at all, and one of them I would not have survived without them. So one of them was very much arrays based. I mean, look, okay, this is a perfect example of why we teach them both, and we require you to learn them both, because one of them was engineering entirely based on arrays. So arrays are often used when we don't have flexibility, and we're going for raw speed. And so that was heaps of stuff I was doing that was doing graphics programming and stuff, because when we work with a GPU, we take an array of memory and we just drop it onto the GPU. And if the array of memory that we created was not exactly the right size for the GPU, it just doesn't work. So you do that exactly the right size, and you put in the information that you have, you drop it onto the GPU, and you ask the GPU to run stuff. And then the other thing that I was doing later on, which was all artificial intelligence, it all had like it had maps like this of possible futures and stuff like that. We were building these tree structures of what can happen in the future, and deciding between those possible futures as the one that we wanted to try to influence to make happen. So game playing AI very much is on this branching possibility of futures, which is exactly the same structure as a linked list, but with multiple pointers. Yeah, so that's I think I love your question, because it was like, okay, how much are we going to use these? And it's just like, thinking about it, my entire computing career would not have survived without either arrays or linked lists, depending on the situation I was in at the time. And I think that you're going to get plenty of other computer scientists that are going to say similar things. However, you are also going to get some computer scientists who are able to say that I didn't need these at all. So, but I'm just trying to think about how many, because I've got another friend whose entire work is, he's a user experience architect. I think he's working with Microsoft. He was working with Microsoft last I spoke to him. It was a couple of years ago anyway. And I'm pretty sure he doesn't do any of this low-level code stuff. What he does is designs the way that people are going to use things. So it's nearly like he could have been just as successful with a psychology degree. than he was with a computer science degree, because he was melding the design of interfaces with what it is that happens in human brains when we try to use things. And I would never argue that his work is less important than someone who's working with, like I did, with like the kind of more difficult. Ooh, I should never say that. It's not more difficult. I think it's actually much, much harder to try to work with human brains than machine brains. Because working with machine brains, they're always going to do exactly what you think they're going to do. Whereas working with human brains, you have to account for all these different types of possible behaviors that humans have. I mean, hop on Facebook for half an hour and you'll see all the different ways that humans are going to act. Plenty of them are not rational, and you have to deal with that. So I was dealing with like, how do I get a GPU to render particular things? And on the other side of things, he was like, how do I deal with the way that humans are going to react to different types of interface layouts? And how do we get an interface layout that works for the majority of people? That's an impossible task, by the way. It never works. So that's like one of the major unsolved problems of computing. Yeah, and so I don't think he works with these data structures at all, because he's at a different level. He's at a much more on the human side of things, and so he would have the interface design, pass it on to someone else who then goes into this back end, and we have charts like this for what is the state of the interface once something happens and something else happens. He would not have to implement it, but he might even draw these things and pass them on to someone else. So you get times where these aren't necessary, and you get times where they're completely necessary. So yeah, I do love your question though. It was like spurred a lot of interesting discussion. Yeah. Yeah, and I think Dean was talking about like, yeah, graphs for stuff like GPS navigation and stuff like that. Definitely, search engines use them heaps. Social media uses this graph structure to, yeah, to decide who's linked to who and stuff, and what you can and can't display to people. Lots of stuff there. Anyway, SK is asking, is over deep nesting bad even if the logic is understandable? I think you've answered your own question there. If the logic is understandable, then it's not over deep nesting. The inherent issue in over deep nesting is that there's no way to make over deep nesting understandable. Because every level of nesting that you go in requires a human to remember one new piece of information about the state of the program. So if I go, if this, well, that meant that I'm in here because I've passed this if statement. That's easy. And then the while loop. So what I'm thinking is, if I'm in this statement, then this while loop runs. So now I'm here in this particular part of this while loop, and I was in that while loop because that if statement was true. And then for each element in the while loop, I'm checking something to be true. So what I'm remembering in my head is, if that first thing was true, then I'm in this particular part of the while loop, then I'm checking this if statement, and then if that's true, then I run this other thing, and then somewhere around there, it's usually around 4, is where what we call the cognitive load of the human brain reaches a point where you have a lot more trouble actually keeping track of where things are. So there's a really, really strong correlation between the level, like just the raw number of nesting. It's usually around 4 or 5. And it's that point at which your average human starts to make errors as to where they are. So for example, if you're in a maze and you try to remember how many times you've turned left or right in that maze, it's usually about 4 or 5 turns in where you won't know where you're aiming by then, because you go, I turned left, then I turned right, then I turned right, then I turned left, and then you're like, okay, am I aiming north, south, east, or west at this point in time? So if you've only made 2 or 3 turns, you're reasonably likely to still remember which way you're aiming, and every time you add another turn to that, there's a chance that you make a mistake. So that's what we think about with over deep nesting, is that you're definitely going to lose something the more things that you have to remember. It's really a human thing. Like, the computer has no problem with over deep nesting. It's got infallible perfect memory. So it knows exactly where it is. It's like, oh, I can see all the conditions that are here in my memory. But it's more about humans not being able to understand it. And us not being able to understand our code is why we then end up writing code that doesn't work, which is the big issue, I think. So hopefully that that answers your question. I feel like you've actually answered your own question, is that nesting is not bad if the logic is understandable. As a rule of thumb, there's a certain level of nesting that makes things less understandable. We can hide things. So, easy example is like me saying that there's a create player, and this does the simple memory allocation, and that is inside this insert player, which is also simple. Well, it's not simple to think about, but it's simple-ish, because it doesn't have to think about creating the player. Something else had to think about that. This thing's only worried about moving the pointers around for the insertion, so we can look at that, and that's easy. And then we insert alpha, which says find a position, and then just call the insert player on that. So these make it easier for us, where I can understand this function even though there's so much code in here because I've hidden it. And hiding things away behind an assumption that they're going to work is much easier for understanding than having the nesting and having to look at it and understand it. So if I don't have to look at it and I can understand it, then my mind can compartmentalize it, and then I don't have to think about it. I won't confuse myself as much. Dean said directed acyclic graph. That, like, those are keywords of those graph stuff we were talking about, where directed means it goes in one direction, acyclic means it can't create loops, and then graph means connected series of nodes. So as you get further into computer science, you will understand what all those keywords mean. And if someone says to you, like, I have a friend who doesn't even say directed acyclic graph, he just, that's a DAG. It's like, dude, that's not what DAG means. But yeah, but he said that's a DAG, and then if he says that's a DAG, then I know exactly what kind of structure he means. It means it's going to flow from the starting position to an ending position. It's never going to backtrack on itself. And it's a graph, so it might have multiple things. A linked list is actually a directed acyclic graph because it goes in one direction, so you can only follow the pointers in one direction, so directed. Acyclic, the pointers never point at a node that was in the list previously, so you never have the next in the list being one of the other nodes that had previously been in the list. That would create a cycle. And it's a graph because it links nodes together. So that's the that's that term. Don't worry about all this stuff. Like, so I just went on a bit of a tangent here with all this stuff. Don't need to know any of this yet. Understand that there are entire subjects, especially this one, there's entire subjects devoted to this that you can take later, where you can spend a whole 10 weeks trying to figure out how this stuff works. Don't expect in this 20 minutes after the lecture hangout that is actually going to have a full understanding of this. But hopefully, because I've taught you the theory of what a linked list is, you're ready to start learning about this, because that's where we want you to be at the end of 1511, is you can go into one of the other courses and see, this is what Mark had been hinting at was potentially in our future. Liang says, if you take the nodes as individual pictures, then assign each node a steering servo output and power output, can use this to run laps around a course using a camera as the input. Potentially. I think that there's a lot more going on there that we'd have to think about. You can definitely do that to certain extents. So there's definitely situations where this thing could be what we call a finite state machine. And in each of these boxes, there is a situation that we react to in a specific way. And depending on that situation, we may go to another possible situation. So this is like go forwards, this is accelerate, and then that's like there's a decelerate somewhere else. And then depending on the situation you see when you're talking about here, depending on the image that you see in your cameras, so your self-driving car, depending on the image you see in your cameras, you may decide whether or not you need to turn and that kind of thing. Yeah. Yeah, like Mealy machines. I think the Mealy machine is like, I can't remember. I'd have to look it up. But it's like a certain form of a state machine. Yeah. Um, Michael asked, how am I finding running online lectures versus in real life lectures? I am thinking about the idea that I will not lecture in person ever again. I haven't decided, but I'm thinking about it. Because, as nice as it is really nice in person. There's a personal connection going on there. And I like to walk around and talk. Like, if you've seen old videos of me, oh, wait, there's very few old videos of me lecturing because the camera on me in the lecture theatre is not what's saved in the videos. So even my old YouTube videos that are me speaking in person don't have me walking around. I like the radio mic. I like to walk around and wave my hands around and aim at things and stuff like that. There is some joy in that. There's some joy in the performance of it. You know, I am someone who worked in theatre, so I obviously love live performance. But in terms of connecting with students, it is undeniably better in the live stream because we've got this, right? We've actually got a conversation happening back and forth. I find that with the tutors in the chat, you get more feedback as well. You can ask your questions in real time and it doesn't interrupt my flow. So if like every single comment that you made in the live chat was you putting up your hand in the lecture, then the lecture would not happen. But the beauty of this is people can ask questions that don't interrupt me. Like I can interrupt if I want to. I can look over and choose to be interrupted, and I'll do that at certain points in the lecture. But it means you can actually ask a question and get an answer while my flow is still going. So I think it is it's just straight out superior to live to lecturing in person. I don't know though. I'm gonna have to decide on this because I think there's also some great benefit in having a human connection as well. So live streaming does have a sort of a human connection, but it's very one-sided. You know, I don't get any feedback from you. I actually had several students in previous terms who I would look at them, and this is probably really, really disconcerting for those students, but I had a few people who would react with their faces. You know, some people really, really react with their faces. I can even remember their faces because I spend so much time looking at them. I would see when they were confused, and I would see when they were bored and other things, and I would tailor my delivery from watching those particular people. So I had a few different people, and I could tell that some people got it more than other people, and I would try to look and see if they were all getting it or not. If they weren't all getting it, I would ease off, and I would try to explain things in a different way and things like that. I don't get that feedback now. I get a little bit in chat, so I could see definitely that during sorry, my phone's ringing. It's no caller ID, so I have no idea. I'm not going to pick up the phone during the lecture anyway. But what was I going to say? That oh, I lost my train of thought. Yeah, in person, I could tailor things to the feedback that I was getting from the audience. But in live stream, I can still see whether the chat's going crazy. So if the chat has heaps and heaps of stuff happening in it, then I know that people are asking a lot of questions about it. So I know I can still kind of get that feedback. What I don't want to do is lose my connection with you as humans. So I think that that's something that if we didn't have social distancing restrictions, what I would potentially try to do is do a mix of the live streaming. I still consider live streaming to be a superior content format for lecturing. I've seen other lecturers are doing this flipped classroom thing where they ask you to watch a video in advance and then they have chat sessions like Zoom sessions and stuff with the students. And I think that might work to a certain extent. I don't think it works for my style. I'm very performative. I like to like to deliver the content. So I think it's a different style from mine. But a lot of the lecturers who are like more sort of these towering experts in the field in research will more likely to be want to like have a video that's well produced so that people like it, and then answer questions using their expertise afterwards. So it's a different style of teaching that I think that I think a lot of the more senior staff are thinking about doing that. Whereas for me, on the other end of the scale, I think I'm more about engagement. So it's like, what's I call it? Like, I prefer the live streaming thing because it's an increased amount of engagement. It's closer to a conversation than a lecture normally is. See how we go, though. We'll see when restrictions start to ease. I would say that the idea of putting 400 people in a lecture theatre is going to be definitely one of the last things in Australia that comes back. I would assume that we're not even going to have the option to lecture in person until there's a fairly widespread vaccine for COVID. Because any other situation, we turn our course into like a super spreader. Basically, we would only need one sick person in the lecture theatre for suddenly 400 people who live in all completely different locations in Sydney to all be under under isolation and things like that. So it'd be super difficult. Yeah, but I haven't made a final decision on that. I've been talking with our teaching admin staff about what our plans are for term 3 and term 1 so far, but we haven't gone any further than that. And honestly, definitely don't see term 3 being lectures in person. Term 1, I highly doubt being lectures in person either. So I'm pretty sure the live streaming thing's going to continue for a while. And when the restrictions lift, then I'll make the decision on whether I think live streaming is a better thing to do, even if we had the option. I had an idea, actually, that I could live stream while delivering in person. So people can turn up if they want to, or they can live stream at the same time. So I'd have to figure out if I can do that. I mean, potentially could work, because like my setup here with the webcam would work if I was in front of a lecture theatre as well, but I wouldn't know whether to look at the camera or look at the audience, whatever. Okay, so Kate was asking, a bit off topic, but that's okay. Where can I go to ask someone about degrees and majors, both majors under the School of Comp Sci? The default point to talk to Kate about that is the student nucleus. They are generic to the whole of the university, but there are some people there that know exactly how we work here in computer science. If you want anecdotal knowledge, you can ask around CSE Soc. So you could ask on CSE Soc's Facebook page and you'll get some information. Know that that information is not official, but it is derived from real experience from people. So you choose the different kinds of information, you'll get different kinds of feedback from that. Yeah, and what Kate is saying there also is that having the tutors here answering questions during the lectures is really good. I've noticed that's amazing as well. But what Liang's saying is it is easier to show your code to us in real life. So if we're there in person, so what used to happen this session right now, where I'd hang around after the lecture, would be people coming to me with their laptops and showing me their code. And I would actually look at their code and talk to them about it. So that's what we're missing at the moment. So we would need to do something with that. Zuhair is saying, how come my insert function isn't a void type? So we've got several insert functions here, but every insert function is returning a pointer to a player. So insert, or even create. Oh, create has to. So the reason why, especially because at the moment this is only returning the same thing that we were given as input, the reason why we're returning something is that we might need to change what the head of the list is. So consider insert alpha. Most of the time the head's not going to change. So most of the time when we insert alpha, the head stays this head. Except there is one instance, which we haven't written code for yet, that we would need to take into account. What if if we're inserting alphabetically and we need to replace the head. So we need to give a new element as head and we shift everything else along. Now our head pointer is still pointed at the second node in the list. We've added a node in and a pointer to it. So we would have to move the head pointer to the new head of the list and then return that. That would be the case where this would change. So if we need to change the head, we want to make sure that what we return from this assert alpha is the new head of the list. Whether the new head of the list is the same as the old head or not, this function needs to decide that. But I don't want to leave this as a void because the head might change. So if we're inserting and it becomes the new head of the list, the head changes. If there is no list yet and this is null, I want to return the new head of the list. So if we're creating the list with the first insertion, then this also needs to return something different from what the head was. We haven't looked at any of those cases in this code yet, so we haven't actually gotten up to that. But probably one of the first things we'll do on Thursday is to look at that, and then you'll get an idea about why this thing is actually returning something. I think Dean was already answering that. Yeah, I think as Dean's saying, we haven't built enough of this yet to know why we're putting all these little things in. We could probably here have this as a void, and we might get away with this actually. Like, you're right, Zaher, in that there is an option here to have this as a void, and we may never actually need it. I think the case that we do need this is if this is null. So if that's null, and we don't return new player, then we will have allocated memory and lost it. So this definitely does need to return something. So if the insert position was null, we have created a node, and we need to return a pointer to that node. So that would replace the list if there wasn't a list there. And if we didn't have this return, then this would be a memory leak, because this would create something and would return nothing. So if we're creating something and we don't have the opportunity to join it up to things that already exist because the thing we've been given is null, if this was null, then we definitely need to return it. So that's a reason why we can't actually get away with this being void, now that I look at it more closely. Yeah. So now that I'm here on the function that you're actually talking about, so yeah, hopefully that gives you enough of an explanation that if we're going to allocate memory, which this create player does, we can't lose the pointer. So we can't have this disappear. So if we don't join it up, so this is if the node exists. So if the node didn't exist, we need to definitely give that pointer back to say, okay, this is the node that we've just created, don't lose it. So if this was null, then we'd have to, in this situation here, we had to save it as the head. Yeah. Cool. All right. I should wrap it up there. Thanks for sticking around, everyone. Hopefully that was some useful information there that we all got. We are going to keep going with this. So there's more to do on Thursday. After we finish the insert alpha, we're going to look at removing people so that we can actually play this game. And we'll also, when we remove, we're going to look at what it means to free up the memory for nodes that we're not using anymore. So we'll be able to free up individual nodes as well as free up the entire list. And I think that's, once we've got removal and memory freeing, then we can play the entire game. Well, after we've finished the insertion. Okay, see you all soon. And hope everyone has a chance to have a quick look at assignment 2 as well. You will find that all the stuff I'm doing now is actually really useful for assignment 2. Okay, see you all later.